Okay, so welcome back, and we are in the fourth, in the first module. We are looking at actually the lecture four. So I'll go get started with this lecture. Let me share my screen. And again, as you know, we will be making a small video of this particular material. The PDFs are also available on this particular web page, and so as your this lecture for you to help you to look at this course. So, okay, so let's get started. So we are looking at in this one, how to interpret LCA, how to do the looking at a little bit of ISO method overview, and at the end we'll talk about some of the green and sustainable materials. So in terms of ISO method, in terms of how to interpret, earlier we have already talked about the goal and scope. So key feature of the interpretation is try to look at the what is the identification of the significant issues. We try to evaluate looking at the completeness, consistency, and sensitivity check, and then we conclude and have limitations. So for example, if you look at this ISO from the ISO methodology, you have a goal and a scope definition, you have LCI, LCIA, and then based on goal and scope, you develop your LCI. From LCI, you look at the identification of significant issues. You find out whether you have the data in terms of completeness, consistency check and all, and then you come up with direct conclusions and which the results can be taken for certain applications. So in terms of issues that we look at based whether in terms of your goal and scope, if you're structuring results of life cycle inventory and life cycle impact assessment in order to identify significant issues, in terms of whether hypothesis that you have taken, multifunctional process, how you are taking care of multifunctional process, what are the processes you are excluding, what is the impact assessment method that you have used. So it's basically ISO standard does not indicate what are the significant issues for a specific case, but it kind of gives you an idea. So in terms of evaluation, we look at the completeness, consistency, sensitivity, additional to the data quality. So in terms of completeness, we make sure that all the relevant information is there. Consistency is that whether the assumption, methods, and data were consistent with the goal and scope. Sensitivity check, one of them is uncertainty analysis. So you look at the reliability of the final results and conclusion and determining how they are affected by uncertainties in the data. So, for example, if you look at the summary of a completeness check, you have option A, option B, material production, energy supply, transport, processing, packaging, use, and end of life. You look at all the data is available here, whether it's a complete, what is the action required in terms of the inventory and all that. Same thing for the option B, whether you have the data, whether some of them are no, and do you have to recalculate, do you have to compare with the option A? So all those things kind of stuff out of there. Consistency, you look at the data source, whether it's a primary data, secondary data, data accuracy, data age, technology coverage, time-related coverage, geographical coverage. So all those things you need to kind of look at. Sources of uncertainty, where it comes from, natural variability of the measured parameters. There could be variability in terms of spatial and temporal. There could be imprecision in measures during data collection. Data gaps could be there. There could be data which is not available, unrepresentative of the data in terms of time, geography, and technical. We simplify the models, and that uncertainties are there. Functional unit allocation, impact assessment method. So there could be some uncertainties associated with that. Many times we don't know. So lack of scientific knowledge, the calculation and the other errors could be there as well. So LCI, these are all coming from ISO documents. So if you have an access to ISO document, basically these are all essentially taken from the ISO document. So you can look it up there as well. So just to summarize, I'll just summarize it in this particular 20-25 minutes video so that you can have a good idea about that. So in terms of lifecycle inventory, the phase of LCA involving the compilation and quantification of input and output throughout its life cycle, that gives you the LCI. Then in terms of impact assessment, you look at what is the potential impact from there. Then you try to interpret in terms of whether the impact assessment or the LCI that you got, whether they are in sync with the defined goal and scope, and whether it is helping you to reach the conclusions and recommendations. If not, then you need to go back and remodify the way you have planned your LCA study. So usually we do a product system and a unit process. Product is basically when you have the elementary and product flows all are together in kind of a box. Unit process is where you have individual unit for individual unit, you have the input and output data quantified. There is a concept, there is a terminology like material elementary flow, which is the material and energy entering the system and leaving the system. That's your material elementary flow. Intermediate flow is the product material energy flow between the unit process. Reference flow is you look at the measures of the output from process in a given product and fulfill the function expressed by the functional unit. So in terms of, for example, ISO terminology, impact category example could be climate change. Your LCA result is amount of greenhouse gases per functional unit. Category indicator, we put that infrared radiative forcing model. We use a baseline model of 100 years of IPCC. Characterization factor is a global warming potential and kg CO2 equivalent, and endpoint is the human health and ecosystem impact. So you look at the LCI data, you compare it with the impact category, you look at what is kind of environmental mechanism is there in terms of the interaction of these emissions, and then you have you try to put a quantifiable representation of an impact category. Its goal is to reflect all the extractions or emission assigns to that impact category. For example, infrared radiative forcing. Then you do the characterization model where you look at reflect the environmental mechanism between the LCI results and the category indicator. So you calculate the characterization factors. Factor is derived from the model based on you convert an assigned life cycle inventory analysis result to common unit. Common unit allows the calculation of category indicator. So then you have a category endpoint, which is human health or ecosystem endpoint. And then you go for sensitivity analysis, uncertainty analysis, you review the LCI results. And there are a lot of other reading material available for you if you're interested to read more about that. So it's very simple. What is the key points of a good LCA? First of all, you need to have a very clear definition of goal of the study. Have a functional unit. This is kind of a summary of what we talked about. Have a system boundary, very clear definition again of system boundary. Data quality is very much important. Multifunctional, how you are going to address those multifunctional process. Impact evaluation according to the goal and scope. Only use renowned and peer-reviewed methods. Must consider the fate and effect of emissions. Test the robustness of conclusions using other methods. That analyze contributions at each phase of LCA, inventory, impact, and evaluation. At each life cycle stage, main contributors. Do sensitivity analysis. So what's an LCA? In terms of LCA is a way of structuring, organizing the relevant parts of the life cycle. You can tool to track performance and perhaps to improve product design. LCA is not a cure-all for all environmental problems. It's not an exact science as well. So it's just an example of, it's just a tool to help us to quantify the environmental footprint. Now, let's look at some of the examples of how it is applied. So this is LCA of NRPAX Plus from cradle to gate. An example is there. So this is a life cycle assessment tool that assesses the product process impacts, environmentally, social, economically. Impact, you can go multiple approaches to LCA, cradle to grave, cradle to gate, cradle to cradle, gate to gate, well to wheel. So there are different, and as per the diagram that you are looking at is the ISO document. So we are looking at environmental aspects, potential impact associated with environmental aspects. So this is the plant located in Vaughan, process MSW from Greater Toronto area and the regions of York, Durham, and Peel. It processes approximately 75,000 tons of MSW per year. They produce this product called NRPAX, which is fuel product produced at Dongera plants, used as a substitute for fossil fuel. Its energy output is 10,000 BTU per pounds, and 60% of the incoming waste is used in producing these pellets. The goal of this study to assess the environmental impact of NRPAX in comparison to medium-grade coal, since NRPAX has similar energy content. The analysis was performed from cradle to gate. Combustion properties and information of NRPAX were unavailable to produce a cradle to grave analysis, so we just use cradle to gate. Chosen function is to provide energy through combustion. So we took a functional unit of say 902 gigabtu was selected to compare NRPAX and medium grade coal based on total input of 75 tons of CO2 of MSW. So that's your process flow diagram. The MSW coming in, truck transport, facility manufacturing, then recycling, then you have the waste, and then it will getting into the truck and going out, and truck transport to finished product, consumers, and other things there as well. Facility assumed to be a black box, only input and output was considered. 70 MSW here, assumed waste was strictly coming to the region for York. Average distance has been taken, collection truck capacity was taken, coal production, cradle to gate analysis, medium grade hard coal briquettes, total MSW sent to incineration or distance travel in coal transportation is identical to that in NRPAX plus LCA. So that's we took that in terms of incineration scenario, same stuff. So this was the MSW composition, and what was the reject was also there. Inner packs, what is the how much organics, how much plastic film, how much paper and cardboard, wood, hard plastics. So they didn't used to use hard plastic, glass, and other stuff. So they're only using therefore the composition of inner packs. What was there in organic waste and what is the percentages, how much metals, paper, cardboards, and other stuff. What is the percent rejection and where the percent rejected material are ending up. So results, we looked at the LCA for inner packs, coal, and then stuff. So analyze this much kg of inner packs, method recipe midpoint H due to organic waste, hard plastics, metals. So you do this analysis, you come up with all these different impact categories. So this is LCA of your inner packs that we got. This is LCA scenario for the coal if you're using medium grade coal. And then this is the LCA scenario if you take the MSW and just burn it directly. So when you try to compare the total inner packs, total MSW, total incineration, total coal, and the impact from the Dongera impact, what we saw that in terms of the environmental footprint with this Dongera plant, actually the environmental footprint was going down. So if you look at the impact on climate change or impact on urban land occupation, again, this product has much lower than if you compare with others. Same thing with the other impact categories as well. So NNPAX has less impact on the environment than coal for most of the impact categories, has a better impact on environment than incineration. Most sensitive impact categories like climate change, marine ecotoxicity, marine eutrophication, ionizing radiation, and terrestrial ecotoxicity. Major contribution to environmental impacts included electricity uses, disposal of plastics, organic waste, and metal. So according to the result, NRPAX is an environmentally positive substitute to medium grade coal, possible alternative treatment of MSW instead of incineration, possible room for improvement in reduction of environmental impact. So results reduction of energy usage, energy audit may be beneficial in locating inefficiency in the production process. Whatever is the leachate generated due to landfilling of rejected plastics, Dongera may want to consider collection and recycle of plastics. Implementation of renewable energy sources like solar panels or supplement required energy, those will be, it's kind of recommended there. So that's kind of give you an example of that part. Now here in the second part is just some theory material, which is just a kind of a reading material. So you can read through that. It is just talking about like when you go for green sustainable material. So we try to, I see when you go for any engineering, you are using several materials. So material has to be extracted, has to be purified. And there are simplest approach in terms of material extraction and refining when you try to go for a footprint is to characterize the footprint associated with the extraction and production to assess materials overall scarcity. So simply stated, if a material is scarce, it is likely to be energy intensive to obtain and refine, and the ability to meet large scale demand will be limited. Elements vary widely in their natural abundance. Like most common elements on the mass basis, ozone, oxygen, silica, aluminum, iron, calcium, magnesium, phosphorus, potassium. So all these elements are present in greater than 1%. So they're widely used in commodity material. Plus some widely used element like silver, tin, it's like antimony, bismuth. They are present at the ppm level or lower on an average in the crust. So some are very less, or abundance is less, and some are quite abundant. So if you look at the gold, silver, their very abundance is very, very small. So annual production of elements for use in commerce, you see that we are producing a lot of elements. Of course, the one iron aluminum, copper are the kind of topping there. So calculate that in terms of, if you look at the ratio of abundance of material to the annual use, if the approximate mass of the crust is this much, based on 40 kilometer thickness and 3 kilometer thickness for oceanic crust. So with an average density of this, so if you look at the abundance, 5.6%, and we use almost so much higher tons per year. So more the abundance, more the usage. Also, you see that for most part. So if all material present in the crust can be extracted, not all material can be extracted. This presents the scenario that everything is can be extracted. Concentration becomes too low to be extracted cost effectively. So there is a relationship between the total crust abundance and economically extractable deposits. So you have to look at the reserves. You may have some things, but what is really to be extractable? Only 1 in 10 to the power of 7 to 10 to the power 9 tons of element in the earth crust is economically viable. Others are not. So if you look at the total crust abundance and the reserves, you see that abundance in crust and reserves in tons. Some of those are reserves in terms of, you can look at the scale here. It starts from 10 to the power of 12 onwards, here 10 to the power of 2 onwards. So reserves is much less as opposed to whatever is available in them as abundance. So in terms of the ratio of abundance to use, economically extractable resource and how much is being used. So you can see that iron ratio of abundance to use is 190 years of iron is still there. But if you look at the way we are using silver, antimony and all that, only 10 years, 19 years, copper 200 years, that's it. So maybe 3, 4 generations after that, copper will not be there. So what does that mean? We have to recycle, reuse, recover. So those are the things that you need to kind of look at in terms of there. So the Sherwood, Sherwood relationship is technology dependent, sometimes referred to as cost of material, largely determined by the cost of extraction. So this Sherwood relationship, where you see that this is the metal price as a function of dilution of the material in commercial. So if you look at the price, platinum, gold, palladium, gallium, silver, they are quite high as compared to, if you talk about iron, chromium, aluminum, and all that. So there's energy burdens on material kind of recovery. You do use a lot of energy to extract the material. Minimum energy, again, entropy. If you remember delta G, T delta S. Delta G is the Gibbs free energy. T is the absolute temperature, and your S delta S is your entropy, which is there. So that we economically recoverable, we kind of look at what is the total as well as economically recoverable, how much is the identified unstressed source. So as there are some recoverable reserve, there are some marginal reserves, some economic reserves, it's there but it's not there, and then the inferred reserves are also there. So you look at what materials are could be there for a quite amount of time, infinite supply, and then there are some which is ample supply, which is highly limited is your gold, silver, copper, ores, like a helium, mercury, tin, zinc. All those are limited supply. So tracking material flow, we have to kind of, materials have a life cycle. So we have to kind of look at how they are moving, uh, where it are coming from, the system boundary, and also the output associated with that. Lead, you can look at some of these examples like lead, how they have moved around in terms of lead. Similarly for the iron, and iron flows. You can talk about iron flows in there. You can flow of other material as well, like global impact of geopolitical issues are also there. So theoretically recoverable and percentage recyclable risk, and how much is the percentage recyclable as well. So very focused. This to Many opportunities exist for recovering material from waste. So we need to try to look at waste resource recovery. And United Nations also looked at some of the recent data on metal recycling and all that. There are what is the energy saving? For how much energy gets saved in terms of aluminum that you can look at material flow summary. So in terms of why these are important is that whenever you are looking at all these different material, when they are used in the environment, they at the end of its life, get thrown away and then they start leaching and other things into the environment. So in terms of their dispersion and fate, persistence, they get uptaken. Human uptake is also there, and the toxicity and other health impacts is there too. So there are persistence of chemicals. They don't go. The chemicals are persistent. They don't go away, and then they create toxicity in the water. So these are some of the examples of what happens when you have these contaminants coming into the environment. For example, here you have a gasoline, which is a leak from the underground storage tanks, and then it goes into the water table. You have a dissolved plume, but then things are also vaporized as per they do get into the air phase as well. Similarly, you can look at this another example of contaminant leaking. Um, Other examples of contaminant. So there you can look at variety of reactions. You can have a look, and then there are some examples like basic definitions or examples are there. I think that's pretty much it. We can, then you can look at this risk and all that, look at some of the basic chemistry associated with that. So let's almost into summarize. Almost every engineering design involves use of material, and these materials have environmental footprint. In this particular module, we summarizes the method for characterizing the footprint associated with extraction, processing, and environmental release. Is the material scarce? Can it be recycled? Do environmental releases have significant impact? So that's those are things we need to look at. There is no universally accepted methods. Multiple methods are used. Energy and engineers will need to consider material in the context of a particular design. So thank you, and I hope again we have gone through a bit fast because that's what like we need to kind of get these done. So we were just going at a bit fast. And it's many of these slides are self-explanatory anyway. So thank you, and I hope it was useful. So again, I'll see you in the next module. Thank you.